So let me revise what we did last time. We defined contour integration. One of the most important technique that you will be learning in the complex analysis course. So we defined what a contour means last time, and then how to integrate a function over a contour that we defined last time. So let me again revise the definition and solve some problems so that the idea of contour integration is clearly understood. So normally we denote contours by letters like C, and are given by the function zt over certain interval a less equal t less equal b. So this is a continuous function and this is of the type xt plus I times yt, because this contour is in C. So this z function is on interval ab to C. That means you have suppose some interval AB, this is called parameter interval, and then if you take a parameter t here and the function z which represents the contour C, then ZA is suppose this point ZA. So A will go to some complex number because Z is a function from AB to C, and B is another point, this is ZB, and as t varies this function is continuous, so we get a continuous path something like this. So this is our contour C and it is traversed from A to B, so we may give a direction like this. So this is called parameter interval of the contour C, and this is the function which gives this contour. Actually this function we always require to do the integration. Okay. Now the integration that we defined last time of the function f. So where is function f now? So function f is typically on the complex plane. So it is in this domain suppose. So this is domain in the complex plane. So this is D, and then f is from D to C. The situation is like this. So this picture, if the camera can capture as a whole, that is this interval, then that interval gives rise to a contour, and there is a function whose domain contains this contour C. So can you see this all? Yes, you can, except for this copy of the complex plane perhaps, which has gone out of the, okay, fine, no problem. So this is the complex plane. So f is complex valued function of a complex variable defined on domain D. So f is from D to C. Now the integral of f over this contour C. So that is the contour integration we defined last time. So integral of f over C is defined as integral from A to B f of zt into z prime t dt. So that was our definition of contour integration. So contour is given means this function z is given, because z is the function that gives this contour, and f is function whose domain contains this contour, so that you can find out f of zt, because these are the values zt. As t moves here, zt traverses this curve. Okay. So and f you can apply at these points because the domain of f contains this contour, and then f of zt goes to C. So f of zt are complex values. Z is also complex valued. So this function is complex valued function of a real variable t. So also is zt a complex valued function of a real variable t, and z dash t also therefore is complex valued function of a real variable t. So this is integral of a complex valued function of a real variable t, which we learned initially. So this is like wt, which is ut plus I times vt. So integral of that will be integral ut plus I times integral vt. Remember that we defined integral of wt from a to b as integral a to b ut plus I times integral a to b vt dt, where wt is ut plus I times vt. So whatever this function comes out to be, you express is at ut plus I times vt and integrate separately, that is integrate real part plus I times integral of the imaginary part. So we already solved one problem. So let's go to the problem number 2, that is on your screen there, that is fz equal to z minus 1. So function is now fz equal to z minus 1, and there are two problems. Part A is you want to integrate this on the semicircle 1 plus e raised to I theta pi to 2 pi. So C is semicircle 1 plus e raised to I theta t, the symbol t is used there, we will e raised to I t, pi less than or equal to t less than or equal to pi. Pi less equal t less equal to pi. So this is contour and this is function, and we want to find what? Integral f or c. What is definition? So you have to first express this contour. So this already given, so this is your zt, this contour is given by the function zt, okay, and then parameter interval is pi to 2 pi, this function is given, so you should just apply the definition now, okay. For convenience, let us see this contour how it is drawn. So it is circle with center at 1 0 and alright, radius 1. So mod z minus 1 will be equal to 1. So it is circle with center at 1 and radius 1. So t equal to pi, if you consider, then you will get e raised to I pi, which is minus 1, that is 0. You get this point corresponding to t equal to pi. T equal to 2 pi, then you will get 1. Okay, so this point. So on this semicircle, you get this semicircle you are drawing, this part of the semicircle. This is circle with center at 1 0 and radius this. Because if you consider 3 pi by 2, okay, t equal to 3 pi by 2, then you will get e raised to I 3 pi by 2, that is 0, cos 3 pi by 2 is minus 1, okay. So you will get, so 1 plus, so let us find out z of 3 pi by 2, that is 1 plus e raised to I times 3 pi by 2, that is equal to 1 plus cos 3 pi by 2 plus I sin 3 pi by 2 cos 3 pi by 2 is 0, sin 3 pi by 2 is minus 1. So this is minus I. So 1 minus I. So you will get 1 1 1 minus 1 point. So this point you will get. So from this to this it is oriented like this. Therefore I have found 3 pi by 2. This is starting point and this is terminal point, this is initial point and this is terminal point, but it may go like this. So some intermediate point I have found. So it is this semicircle that we are integrating on. Okay. Anyways, the formula for FC is already given. So ZT is given by 1 plus e raised to IT. So by definition, integral of f over c is integral over the parameter interval, that is pi to 2 pi. Then f of zt. So this is f. Here you have to substitute this zt, that is 1 plus e raised to it. So 1 plus e raised to it minus 1. So have you understood, this is fz for any z in the domain of f. But now f of zt you want to find. But zt is 1 plus e raised to it. So in z, in the domain, in the definition of f, I put zt in place of z. So this is f of zt into z dash t. This is zt. So z dash t is I e raised to it. I e raised to it dt. Now this one will get cancelled and I will come out. So I times integral pi to 2 pi e raised to it into e raised to it, that is e raised to 2 it dt. Now see that this integral, can you guess what this integral will be? Without even writing further, can you tell what the value will be? Because this will be cos 2t plus I sin 2t, and then integral of cos 2t will be in terms of sin 2t, but sin 4 pi and sin 2 pi will be equal, and similarly cos 4 pi and cos 2 pi will be equal. So this integral is going to be, yes, this integral is going to be 0. This integral is going to be 0. Let me write, this is I times cos 2t plus I sin 2t, integral from pi to 2 pi dt, I times cos, so integral is sin 2t upon 2 minus cos 2t upon 2, but pi to 2 pi it will be 0. So I will directly write this 0. Just verify later on maybe if you want that the integral is 0. The second integral, the second problem, the function is same, that is z minus 1. The contour is changed. So contour is now the segment from 0 to 2 on the real axis. Segment from 0 to 2 on the real axis. Where is this? So now the definition of contour you have to write first. Okay. So I got the duster, that was I was looking for. Alright. So the line segment is from 0 to 2 on the real axis. So this is 0, this is 2. So what is line segment from 0 to 2? Yes, it is 1 minus t, last time we saw in one example, the initial point plus t times terminal point. So your zt here will be, this is 0, so 2t, 0 less equal t less equal 1. 1 minus t times a plus t times b is always a parametric representation of a straight line. We solved one problem last time. Okay. So now the initial point is 0, terminal point is 2. So this is straight line from 0 to 2. You put t equal to 0, it is 0, t equal to 1, you get 2. So this is now zt. F is given, zt is given, apply definition, f of zt into z dash t dt we have. So now integral over this contour is, so integral f over c is 0 to 1 because that is parameter interval, 0 to 1, okay. F of zt, f is z minus 1 and zt is 2t. So 2t minus 1 into z dash t dt. So 2 dt. It is done on the next page. Yeah. So 2t minus 1 into 2 dt. So this is equal to, what is integral of 2t? So this is 2 is outside. It is t square minus t from 0 to 1. So it is 1 minus 1, 0 and 0, 0, it should be 0. So again the value of the integral is 0. Okay. Maybe let us solve one more problem, which I will write, which is not written there on the notes. Let us write one more problem, which is not written on the notes there. So you can take down. So it is from the exercises in Churchill. Okay. Fz is defined by the equation. Fz is defined. I will write it here. Fz is defined by Fz equal to 1 if y is negative. Fz equal to 1 if y is negative and equal to 4y if y is positive. If y is positive, it is 4y. If C is the arc from Z equal to minus 1 minus I to 1 plus I along the curve y is equal to x cube. So C is arc along y is equal to x cube from minus 1 minus I to 1 plus I. Minus 1 minus I to 1 plus I. You may take down this problem. Function is given by this and arc is this. So we have to find parametric representation of the arc, and then once you have zt, that is parametric representation of the arc, the function is given, you have to integrate then. So let us see how this arc looks like. So you have to draw y is equal to x cube. So Can you draw the curve y is equal to x cube in your notebook? Can you draw y is equal to x cube? Please draw. So 1, 1, minus 1, minus 1. So 0, 0. So y is equal to x cube is like this. Okay. The rough sketch of y is equal to x cube. And you have minus 1 minus I, so this point, and 1 I, this point. So this is 1 plus I, that is 1, 1, and this is minus 1 minus I, that is minus 1 minus 1. So this is the arc that we want to integrate. This is along curve y is equal to x cube. Now value of this function is given on the basis of y, that is y coordinate of z is positive. So here y coordinate is positive, here this side. So there the function is given by 4y, and it is 1 if y is negative. So from this part the function is has some value. So at 0 also y is equal to 0, this point also one has to define. So let us take that to be 0. So suppose it is 0 at y is equal to 0. Okay. Now the arc is y is equal to x cube. So can you parameterize this arc? That means this arc you want from some specific value of t in a closed interval. So it is y is equal to x cube. So y coordinate is x cube. So if you take x equal to t, then y is t cube, because x is t, then y is t cube. Understood? And then you want x to range from minus 1 to 1. So the arc is given by zt equal to t, x coordinate is t, plus I times t cube, because y is x cube. So if x is t, y has to be x cube on the curve. So this is exactly the parameterization of y is equal to x cube. But we want only from minus 1 minus I to 1 plus I. That means x, which we have taken as t, ranges from minus 1 to 1. So minus 1 less equal t less equal 1. So this is our description of the contour on which we want to integrate the function. Okay. So now integral of f over c is integral minus 1 to 1 f of zt into z prime t dt. That is our definition, that in place of z you put zt, and then you have to do that z prime t dt. Okay. So what is zt? It is f of t plus I times t cube. But then what is f of that is according to how f is defined. Okay. Is this clear? So let us consider this first, minus 1 to 1, okay, f of t plus I times t cube. This is f of zt into z prime t dt. Z prime t is what? 1 plus 3t square I times 3t square dt. How to find f? The definition of f is given, that if y is negative, now what is y here? That means this is x plus iy. Okay. So this y coordinate is t cube. So when t cube is negative, its value is 1. But t cube is negative if and only if t is negative. That means minus 1 to 0, this f will take value 1, because, so you can show this again, this part. The value of the definition of the function is fz is 1 if y is negative and 4y if y is positive. So this we have to split into two parts, minus 1 to 0. On this will be just 1, f is 1. So 1 plus I 3t square dt plus 0 to 1, because 0 to 1 y will be positive and then value will be 4y, that is, it is 4t cube. Is this clear why it is 4t cube? Because if z is x plus iy, fz is 4y, but if now you are applying on zt, so y coordinate of this is t cube. So 4y means 4t cube into 1 plus I 3t square dt. Now it is easy because you separate this into real and imaginary parts, that is 1 plus 3t square, okay, 1 plus I times 3t square, integrate both. Similarly 4t cube and I times 12t raised to 5 separately integrate. Okay. So you want to complete this problem? Do this. This will get into two parts, real and imaginary parts, that is 1 dt, minus 1 to 1. Understood? 1 dt plus I times 3t square dt, that is t cube, minus 1 to 1. So this will be over. This is 4t cube dt 0 to 1, first part, plus I times 12 t raised to 5 dt 0 to 1. So just complete this in 1 minute, okay, find the answer and write down in your notebook. I would have said tell me, but then you can't tell me. So just find out the answer. Finished? Okay. Now on your screen you have a theorem and several properties of the contour integral are stated in this theorem. See, whenever we have some definition, so like you learned Riemann integration in the last semester, and then whatever properties of Riemann integral you stated, that is a to b plus b to c is equal to a to c, okay, integral of f plus g is equal to integral f plus integral g, and several properties of the integral you learned. Now we have defined contour integral, so basic elementary properties once for all we should list out. That is what I have done in this theorem which is there in front of you, that is the first statement you read, that is the value of the integral fz dz is invariant under reparameterization of C. This is important point. So let us see what does this mean first of all, and then see the proof. Okay. See, we have integral of f over C, where what is C? C is some contour. C's contour means what? That it is some curve like this. That means what? It is given by certain interval. So some parameterization is there. So these are points zt. Now instead of this parameterization, if you have some other parameterization of the same curve, that is on CD suppose. So suppose this is u, parameter is u, and some other function wu suppose, this is zt, this is wu, okay, but they give rise to the same curve suppose. The curve is same. Do you see this? The curve is same, but only thing is that the parameter interval and the parameter function that is used to describe the points on the curve are different. We saw this once when we proved that the length of the contour is equal under the reparameterization, and then at that time I gave you two parameterizations of the same curve, that was I think semicircle. So you may parameterize a certain curve in variety of ways, but the curve is same, so some intrinsic properties of the curve will remain same. Like the length remains same. Here we have said that the integral of a function over C remains same whether you use this parameterization of this. That means if you use this parameterization, by definition it is equal to what? Integral a to b, because now this parameterization is on a to b, f of zt into z prime t dt. So apparently this depends on the parameterization, because we have used a to b everything. But now the same curve is described suppose on CD, and then the function is wu, then this should also come out to be integral from C to D f of wu into w prime u du. Because suppose only curve is described, that suppose it is a semicircle or it is a parabola. We may use two different parameterization. Somebody may take this interval, somebody else may take the other interval, and the function also you may use to describe the same curve will be different. But then first person who is using this, his integral will be on AB, and the other person who is using this parameterization, his integral will be on CD. Further, the function zt and wu also could be different. But this contour integral, the function remains same that we want to integrate, and the contour remains same. So the integral we wish must remain same, and that happens. That is, these two quantities are equal. These two are equal. This equal to this. Clear? That is f of zt into z prime t dt is equal to f of wu into w prime u du, where zt is one parameterization and wu is other parameterization. The proof of this is actually simple, and it is given there. All right. So that is what is written. So do you see on your screen the proof part, that is and number 1, that let zt a less equal t less equal b represent the contour C, and phi be continuously differentiable function which maps CD onto AB with phi dash u positive, then wu z of phi u is another parameterization. So in this situation there is a transition map which goes from this interval to this interval, that is phi, and then suppose phi dash u, that means as c varies from u varies from c to d, t varies from a to b. That means phi dash u is positive. That is phi is increasing. Phi is increasing. That is as u increases, t increases. And phi u equal to t actually. Okay. Phi of u is t. So this parameter, so phi of u, and then you may apply z. Okay. So wu is actually nothing but z of phi u. Have you understood? This parameterization is used means there is some function which will carry CD to AB and phi u is t. So that means it is as if substituting t equal to phi u. So zt will become z phi u. So once you go on AB, you apply z now. So you get this curve, and then w is the parameterization of the curve, other parameterization. So two parameterization will be related by some transition function like this. Now you can just substitute in these quantities, that is, what is f of wu? So it is f of z phi u into w prime is z prime phi prime u du. Okay. So you can just see this on the next page. So then integral or c fz dz, do you see on your screen? Can you see on your screen? That is integral fz dz over c is c to d f of z phi u into z prime phi u into w phi prime u du. Okay, c to d f of wu is z phi u into w prime u is z prime phi u into phi prime u. Okay, which is equal to actually f of wu into w prime u. Okay, so this if you start with and put t equal to phi u, then it is f of z of phi u. Now zt will get convert zt equal to phi u. So in this put t equal to phi u. So actually the proof is put t equal to phi u. So z prime t will become z prime phi u into phi prime u. Okay, that is what is written there. Z prime phi u into phi prime u. And f of zt, but t is phi u, so f of z phi u will come. Okay, but then z phi u is wu, so f of z phi u will become f of wu, and then z prime phi u into phi prime u is w prime u. Okay, so this is, these two will be equal. So if you want to just see that these two are equal, put t equal to phi u and use this relation, that wu equal to z phi u. Okay, the proof is written there, so you may just go through again for a minute. So if you use the same curve and use two different parameterization, then value of the contour integral does not change. It is invariant under reparameterization. Okay. So that was proof of the first statement. Proof of the second statement is, so let us see what is second statement. Now can you see statement 2 of the theorem on your screen? It is integral fz over c plus or minus gz is integral fz plus or minus integral gz. Okay, this should be obvious from the definition of the contour integral. Okay, just see there. Once zt is given, so the second property that is written on your screen there in the theorem. See, all these properties are used later on in evaluating the integrals. Okay. So, integral over C fz plus or minus gz is equal to integral over C fz Is this clear? Just apply the definition. So, let us consider this right hand side. Okay. So, right hand side is nothing but what? Integral. So, suppose C is given by zt. So, this is a to b f of zt into z prime t dt plus same curve is there. So, that is also zt. So, a to b, but the function is gz. So, g of zt into z prime t dt. Now, this is property of the complex valued function of real variable, that on same interval a b, if you have two functions w1t and w2t, then you can add these two. So, this is nothing but integral of f of zt plus or minus here g of zt into, both terms are multiplied by z prime t. So, z prime t dt, and that is nothing but this by definition. That is nothing but fz plus or minus gz over c, because this will be fzt plus or minus gzt into z prime t. That is this. Statement number 3. On your screen is z naught fz equal to z naught into integral fz. That also should be obvious. So, now you just go through the proof. I will not speak anything for 1 minute. So, proof is there on your screen, you just go through the proof. Okay, so let us go to the next part. Okay, so statement number 4, integral of fz over minus c is minus of integral of fz over c. Okay, and the proof is written there 4, so let me explain that. If you remember last time we defined the curve minus c, that is if curve c is given like this, then the exactly opposite, so this is c, then opposite orientation if you give to this, then it is minus c. In terms of the function zt which parameterizes the curve c, if zt gives the curve c, then minus c is given by z of minus t, and if the parameter interval is a to b, then minus b less equal t less equal minus a. That is how minus c was defined. Once you have definition of minus c, you should be able to integrate over minus c. What will be this? This is equal to, what is parameter interval of minus c? Minus b to minus a. So you integrate from minus b to minus a. F of z minus t into derivative of this, that is minus z prime minus t dt. Okay. Now, if you put minus t equal to u in this, then you will have f of zu into z prime u du, okay, and this minus sign will be there, but minus dt will be du, and this in this limits will be when t has value minus b, u will have value b, and then this will be, this minus sign will change this. So you try that. This is nothing but a to b f of zu into z prime u d with a minus sign. Okay. Shall I tell you this again? Integral over minus c is minus b to minus a, because parameter interval of minus c is minus b to minus a. Definition is f at the points of the curve. So f of z minus t into derivative of this, that is z prime minus t into minus 1 dt. So this minus sign anyways come out. Now put minus t equal to u. So you will get f of zu, z prime u dt equal to minus du. So you will get this minus minus plus once, but then you will get du. But when you put t equal to minus b, you will get u equal to b, and then this a. Then to change a to b, you will get one more minus sign. So this is integral of f over c minus sign, because now this is from a to b, so this is over c. Okay. Next property is statement 5 on your screen now. Fz c1 plus c2 is integral fz over c1 plus integral fz over c2. Okay. So let us see how to prove this. In fact, the proof is written here on your screen. So C1 is the contour given by Z1, C2 is the contour given by Z2, then we know how to define C1 plus C2. Okay. So let me use this contour. Do you see some other board now? So if C1 is the contour Z1t, A less than or equal to T less than or equal to C, and Z2t is C less than or equal to T less than or equal to B, then we have defined C1 plus C2 as ZT on A less equal T less equal B with ZT equal to Z1 T on AC and equal to Z2 T on CB. This was definition of C1 plus C2. Okay. So see this definition of C1 plus C2. For this we need at point C, which is common in the domain of both Z1 and Z2, we want what? Z1C must be equal to Z2C. So these curves should be so that Z1C is equal to Z2C. Now once we have addition of these two curves C1 plus C2, and if a function is given, say f, and on this curve if we integrate f, what do we expect? This integral we expect as integral of f over this curve C1 plus integral of f over curve C2. That is what is stated in the theorem, and the proof is given there. Okay. So proof is straightforward once you know the definition. Okay. So obviously write the right hand side. So what will be integral of f over C1? By definition you use the parameterization for C1. So RHS is nothing but integral from A to C, because we are integrating on C1. So it will be from A to C. So A to C f of Z1t Z1 dash t dt. That is exactly the definition of integral of f over C1. Plus integral of f over C2 is what? It is C to B f of Z2t into Z2 prime t dt. Now you have to apply the corresponding property for real valued functions of real variable. To see this, see this is complex valued, but this anyway will get split into say ut plus I times vt, this also will get split. But this is on interval A to C, this is on interval C to B. So this will be, this can be combined and can be written as integral from A to B. What will be the point at which f will apply? So on AC f is applied on Z1, and on CB f is applied to Z2t, but that is how we have defined ZT. See this, ZT is Z1t on this and Z2t on this. So this means that if I write A to B f of ZT, it is exactly these two, but Z1t and Z2 dash t is Z dash t. Because Z dash t, ZT is Z1, so this will become Z1 dash t on A to C, and Z2 dash t on C to B. So this is exactly Z dash t, but this is nothing but integral over C f. This is exactly integral over C. So integral over C1 plus C2 is integral over C1 plus integral over C2. How to use this property? This property is used, can you see one more board? Okay. So how many boards do you see now? Okay. At a time only one maybe in camera. but there are 4 boards, alright. So, camera may not be able to capture if I write here now, okay. Can you? That is good. So, that is board number 1, board number 2, board number 3, do you see 4? That is good, just some fun maybe. So, there are 4 boards. Now, I am writing on board number 3, alright. So, next property is that you see the next on your screen 6. This is very important property, that is there is some bound on the integral. So, if mod fz is less than or equal to m for some positive constant m, then modulus of the integral is less than or equal to m times L, where L is the length of the contour C. Okay. So, see this integral of f over C, its modulus is less than or equal to m times L, where what is m? M is upper bound for f on C. So, mod fz is less than or equal to m on C. And what is L? L is length of the contour, length of C. So, integral has this bound. See, this is a complex number, complex contour integral, this is a complex number. So, this complex number will be less than or equal to m times L, where m is upper bound of the function f, in the sense that mod fz, fz is a complex number, so there cannot be any bound, but mod fz is less than or equal to m on C, and L is length of the contour, alright. So, how to prove this? So, the proof is given there, proof is there on your screen. So, let zt represent the contour, okay. So, integral of fz over C is this, alright. So, just follows from the definition. So, let us start with the left hand side, integral mod of fz, okay, but this is integral from a to b f of zt into z prime t dt mod. But if you remember, last time we proved that if this wt is a function, then mod of integral wt is less than or equal to integral mod wt. So, this will be less than or equal to modulus of the integral is less than or equal to integral of the mod fzt into z dash t dt. Now, mod fzt is less than or equal to m. So, this I can certainly write mod of this into mod of this. But this mod fzt, that means f is taking values on the curve, because this is curve, this is the contour C. So, this is less than or equal to m. So, the entire part I can take out and say less than or equal to m. So, this is less than or equal to integral from a to b, okay, m I will take outside, and mod z prime t dt. But this is exactly the definition of the length of the contour. So, this is equal to m times L. So, this inequality follows. Modulus of the contour integral is less than or equal to this. Okay, so this these proofs we have seen, and now we want to see some more points, and then we want to see some problems that we will do in the next lecture. Okay. So, we saw some basic properties of the contour integral and saw some elementary so simple problems of